to introduce you to our tutor, Marija Mitrovic Dankulov. She's a research professor, head of Innovation Center at Institute of Physics, Belgrade, and she will hold the HPC application in analysis of large-scale complex networks. Enjoy.
Thank you very much. Hello, everyone. So I don't know what is the idea, if people can ask questions during the talk in Q&A probably or something like that. So there are going to be a small break in some sense. So there is two different parts of the talk, and I'm going to use this time to answer your questions if you have them after the first time, and then I will also answer questions in the next after the end of the talk. So just shortly, as colleagues said, my name is Marija Mitrovic Dankulov. I'm a research professor at Scientific Computing Laboratory here at the Institute of Physics Belgrade, and I'm also head of Innovation Center. So I'm very much involved in collaboration between the industry. But in general, I'm a physicist that study complex systems using predominantly a complex network theory. So that's why my focus is actually on large-scale network analysis. Besides this, I'm also involved in our National Center of Competence for high-performance computing, high-performance data analysis, and AI. This is funded by European EuroCC for Southeastern Europe projects. And I'm also having a small role in one startup here in Belgrade as an AI lead, but basically I'm doing data science there. The reason why I wanted to talk about this is that for a long time, as a scientist working in complex network theory, we use different kind of C modules in C, in C++, but for the last 15 years, the development of Python kind of brought development of module, a very specific module for analyzing complex networks called Networkit. However, this module, while very useful in the sense that you can very fast find the solutions for the problem you're looking at, so you don't have to write the whole code for your network and your network analysis. It's in Python and it uses CPU basically, and it's not parallelizable, and it's it can be very slow and very hard for large-scale network analysis. So usually you're very limited using Networkit. So for these reasons, I wanted to actually show you a new module, relatively new. It's few years old, that was kind of built on Networkit as an idea, but it uses C++ and often uses OpenMP, MP for shared memory parallelism, and allows more efficient codes and more efficient way of actually analyzing this large-scale data. Here's the link to this module, and as any module in Python, it's actually open source. So this means there is an open community that also develops this code, and they're always looking for people who would like to contribute. So maybe some of you would be interested in the future to do exactly this. And as you will see, there are certain things that still need to be worked on and so on. So I learned from my mistakes. I already gave similar talk to this on one HPC event, and I realized that people actually don't understand what networks are. So a complex network is a system, or it's a graph in mathematics. It's a mathematical object that actually represents nodes and edges. So nodes are usually like kind of point elements in the system that are connected in some specific way. For instance, in a social system, nodes would represent people, and edges would represent the relationships with these people. This can be friendship relationships, it can be professional relationships, it can also depict, for instance, communication between people. Depending on which part of the social system you want to represent, your edges will be that specific, will represent that specific relation. In biology, you can also represent systems with networks. For instance, in protein-protein interaction networks, proteins are represented as nodes, and interaction between proteins are actually represented by edges. These are very simple examples of complex networks. You can have much more complicated representations. You can have networks that are changing in time. So we usually use temporal networks in this case. You can have, in one system, you can have relations of different types. So if, for instance, you can have a social network where people can either be friends or they can have professional relationships, but also these relationships can overlap in some sense. So in this case, we are talking about so-called multiplex networks. So basically, we have a layered network with different layers where each layer represents one type of interaction between people. And there is a whole science that was developed based on this for the last, so to say, 20 years, okay? But here I'm going to keep a very simple case. So I'm going to keep with very, very simple networks. And these networks basically have relationships that are of the same type, very simple nodes. So nodes belong to the same type of entities. And also these networks are non-weighted, so they're binary, and they are undirected. So this means that there is a relation between 1 and 2, and there is also the same relation between 2 and 1. Sometimes people think that actually friendship network is something that represents this kind of relations, but actually it's not. It was found that friendship network is very often undirected, directed. So this means if I consider one person that my friend, it doesn't mean that that person also considers me as her or his friend. So, but in this case, we will have a very simple solution. So first thing, I'm using Google Colab for this because it's easier for me to use their GPU infrastructure. In this case, I'm using the T4, which is available if you don't have a professional account on Google Colab. You can still use it because this is free of charge. So it's easily available with non-paying account. And we first need to actually install Networkit. It's not installed by default in Google Colab. And also, there are certain elements, there are certain models that we will use in this case. I like to have, of course, I have to import Networkit as NK. Matplotlib is not necessary in this case because Networkit doesn't, at least plotting in Networkit doesn't work good for under the Colab that I discovered later. Of course, NumPy and SciPy are always necessary for some calculations, and typically as people who use and work on data science, Pandas is kind of must-have module that allows you to import different kind of documents. So here we have a very simple network that consists of 10 nodes. So this network is currently non-connected. And I want to show you how you can use Networkit to actually, if you have a picture of this network, how you can enter your nodes. And what you will do is, so we will import the modules. You will first have to define an object, a graph in Networkit. The people who use Networkit for this kind of stuff, it's the same syntax. So basically what you do is define an object, and now your object is actually empty. So there's nothing, there are nodes, there are no edges in this graph, and now you can actually add a node. So first we will add one node. interesting thing is that the function add node actually doesn't allow you to add a node of specific index. You actually go from 0 to n. So basically, it doesn't allow you to skip nodes, which is compared to the Networkit, a little bit different situation. In Networkit, you're allowed to do this kind of stuff. Here, not. And also, there is a function when you can exactly say how many nodes you want to add to your network. In this case, we already added nodes with index 0, and I want to have here 10 nodes. So I will also add additional 9 nodes. What I want to say also is that actually index goes from 0, so it doesn't start from 1. So you need to be careful with this when you're using a Networkit. And here we have, we can actually see how many nodes we have in the network. And as expected, our network actually has 10 nodes. Now I want to also check how many edges I have. In this case, because I didn't add any edges, I have 0 edges as expected. Now I can also add edges in my network, and this is how my network I would like to look like in this case. And I will add first, for instance, the link between node 0 and 8. So this you can do as only a single edge in that sense. So you can look at, so basically what you will do is use the function add edge, and then you add, you give ID of the node 1, and then you give the ID of the node 2. So basically you show the link, and this way you actually add one edge, and the function actually gives you back true as an information that this link now exists in the network. And really, if we look at number of edges, we see that we have one edge. Now I only wrote this network by hand basically, and I added these edges that exist on this picture, and based on this I will add all of them, and now I have 15 edges in my network. Be careful if you repeat any of these edges, you actually will add formally one more, and the number of edges will actually count each of these duplicates as one additional edge. So basically we will not have the exact number of edges in the system. And now we can also, if you already have a function and a graph and you want to check whether your nodes exist in the network or your edges exist in the network, you can use a function hasNode, and it can check, it says true. But for instance, if you want to see whether we have a node of index 10 and run this, we will get that we don't have it, and then it's false. The same thing can be done with edges. So basically, if you check whether we have edge 0, 1, this is this edge, the function says it's true. But of course, if you want to look at 0, 9 edge, we will see that actually our system says that we don't have this edge in the system. What is an interesting thing in network theory, there are many properties of a network that we can look at, and each of these properties are telling us something about our network. The most common, the most used, the most frequent property, and probably one of the first properties that scientists calculate in their networks is the degree distribution. Degree is the number of first neighbors a node has. For instance, in our case, node 8 has 4 neighbors, 0, 6, 3, and 9. Okay, so the degree of node 8 is actually 4. And really, there is, of course, a function that can tell us this. 0 node also has 4 neighbors, as we can see, 1, 2, 3, 4. And if we ask a function called degree, and then we give the ID of the node for which we want to find out how many neighbors it has. We will get an information that here it's 4. Now you can write a for loop and calculate that for each of your nodes in the network. But of course, this is really inefficient. And luckily, Networkit has its own function. Unlike Networkit, which has usually a degrees of nodes, and then you get the whole information, here you need to use a degree centrality. And this function is actually slightly different for people who use Networkit. It's calling this function is slightly different than in the case of Networkit. In Networkit, you only write one line of the code. Here you will have to actually assign an object, calculate degree centrality of the network. The function belongs to centrality class of Networkit, and then you need to run it. And after that, you actually get the information about degree centrality of your nodes. But to collect the information about this, you have to use actually a scores function. So this function actually gives you back the degrees of your nodes. And now if we look at, we actually get a list of degrees for each node. This is a 0th node, and of course it has degree 0. This is node 1 and node 2. And if we go back, we see that node 1 has degree 2, and node 2 also has degree 2. In our case, degree 3, the node 3 has degrees 1, 2, 3, 4. And really, if we go back, we see that this is the case, and so on, okay? So basically, degree centrality here actually represents a degree function. And what we usually do in network theory is that we want to see what is the number, or how this degree distribution function actually looks like. Because if we look at some random networks, there the degree distribution represents Poissonian distribution. So this means you can define the average and standard deviation in this function, and you can actually find a typical representative of nodes in the sense of degrees in these systems. Unlike them, the real networks actually have a power law degree distribution. So this means that and you will see it later when we actually analyze a large network, how this power law degree distribution actually looks like. But here, just to tell you, is that in this case, we have very large number of nodes that have relatively small number of degrees, so small value of degrees. And then we have a long tail in this distribution, and there is non-zero probability that we will have nodes that have very large number of first neighbors. Of course, our network here is quite small, so it's not that interesting to look at from this perspective. But one of the ways to do this is actually to look at ranking of degrees. So this can tell you a lot about whether the function is power law or not. So I will sort our list, and after sorting it, of course, and I'm sorting it in the way that I'm starting from the largest ones toward the smallest values. I have to transfer it to array to actually plot it, and then I will also rank or assign a rank to each of these degrees to plot a ranking distribution. And again, rank I will transfer to array function to actually use it and plot it on a graph. And as you can see, we basically have 1, 2, 3, 4 nodes that have we have one node that has degree 1, And then we have 1 and 2 nodes that have degree 2. And then we have 1 node, 2 nodes, 3 nodes that have degree 3. And then in the end, we have 1, 2, 3, 4 nodes that have the degree 4. So basically, this is how we look at this. Actually, when you have a very large network, this rank function follows so-called zip law, and then you can actually fit it, and it's again this zip law actually is a power law, and when you fit it, the exponent that you get in the zip law is related to the exponent of your degree distribution as +1. So basically, this way you can actually calculate the number of the slope of your power law degree distribution, and this can tell you a lot about the heterogeneity of your network. So typically, networks in a real world system that have degrees between 2 and 3 are usually real networks. In the case of real networks, this exponent is between 2 and 3. And this shows us that typical real networks are very heterogeneous. They have a standard deviation of this degree distribution is doesn't tell you much, or no, standard deviation is actually in limit of large networks, so like infinite large networks, is actually diverging, so it's not a typical one, and mean basically doesn't tell you much. So this means that in these networks you cannot select a specific representative of a network, and you have to use different kind of approaches to analyze this network. You cannot use a mean and standard deviation to actually conclude much about the properties of these networks. So you have to be kind of inventive in this case. The second property that is also very important for complex networks is a clustering coefficient. And clustering coefficient actually tells you, for each node, you can calculate the clustering coefficient. And this clustering coefficient tells you the probability that 2 neighbors of one node are actually also neighbors, okay? So basically, what we have here is just an example. For instance, for node 5, this node has neighbors 6, 3, and 4. Its neighbors each also form links with each other. Okay, so we usually say that this is a motif of size 4, it's a clique. And in this case, the node 5 actually has a probability 1 that its 2 random neighbors are also connected with each other. Okay, for 8 and 0, these clustering coefficients are going to be lower than in the case of node 5. But you get the idea. So what we are basically doing is that we know the degree of the node, for instance, 8, so it has 4 neighbors, and we actually calculate the number of existing links between its neighbors, and we divide this with the maximum number of links that can exist between its neighbors, and that's actually its degree times degree minus 1 divided by 2. So this is the number of total, or the maximum number of links that can exist between the neighbor of that node, and this is actually gives us the clustering coefficient for each of these nodes. But of course, instead of only looking at how to say this, a link clustering coefficient for each specific node, we can also look at clustering coefficient of the whole network. And Networkit actually gives us an opportunity to calculate both of these things. So it gives us functions for this. One of them is clustering coefficient. Actually, for For clustering coefficient of the whole network, the class is globals. And then when you call this class clustering coefficient, you of course have to call this. And then there is several options that you can use. In this case, I'm using exact global because my network is relatively small for this. But if you have a really, really large network, you can go to Networkit site and actually look at what are your options for this. You can use some approximate values, and it can give you, you can even give it a number of iterations that you would like to have during this process. So you can actually control the time that you need to calculate this. You will not get the exact value in this case, but you will get something that kind of approximates your clustering coefficient. In our case, this clustering coefficient is 0.6. Just to tell you how important this clustering coefficient is for us, we usually say that social networks have a relatively large clustering coefficient. The clustering coefficient both for nodes and the whole network goes from 0 to 1. This clustering coefficient for network is actually average of clustering coefficients for each node in the network. And what is this telling us is that our network actually has a very high probability that nodes that are connected to one node will also be connected with each other. So this means we have a large number of triangles in the network. And it also tells us, for instance, for social networks, it shows that this clustering coefficient is quite high. Actually, I didn't see a social network that has clustering coefficient larger than 0.6, 0.7. This is already very, very high. And usually, for instance, Facebook has this kind of property. But for instance, for biological and technological networks, this is not the case. What this tells us is that in social networks, people have tendency to close these triads. So if I have two friends, I'm going to go out with them together. I'm going to introduce them with each other. Probably there is similar interest if I'm in companion with both of them. And there is a high probability they will also make a bond with each other and actually become friends too. In biological networks and technological networks, this is not the case. So they usually have a very, very low clustering coefficient. And typically, if we would look at the infinite network limit, this clustering coefficient would be diminishing or would go to 0. So this is a kind of interesting difference between social and technological and biological networks. And also Networkit also allows us to actually look at local clusterings, and this is set in centrality class subclass of Networkit. And you can actually, the same for centrality, degree centrality, here local clustering coefficient is called, and then you can actually calculate. So basically you call the function, you run the function, and then you're looking at the ranking of this function, and then it gives you, in this case, doesn't give you for node 0, but it gives you for other nodes how is the link of or the clustering coefficients for each of these nodes. Actually, it gives you for 0, but it starts from the largest clustering coefficient toward the smallest one. Here we see that 9 actually has a probability of 0, which is kind of expected because 9 only has one friend or one connection, and there is no possibility for that node to create a friend for 8 to create friendship with each other. So basically, in this case, by default, we put 0. Node 8 is kind of relatively low connected. Has a low. It's good connected, but has a low clustering coefficient because its friends are actually only making one triangle, so between 3 and 6, and the rest of the friends don't create links, and so on. Okay, so it's kind of interesting aspect of a complex network. And then there is another thing that you can look at complex networks, and that's a network distance and diameter. So this is one of the first properties that were actually looked at in social network and then in the rest of the complex networks. And it kind of steered the whole idea about complex network structure and the idea of creating new models that will kind of limit or imitate this behavior in specifically social networks, but also most of the complex networks that we are looking at that are not necessarily embedded in physical space, they have very, very small diameters. So we usually say that most of the real world networks have small world property. So this means that the maximum distance between two nodes grows logarithmically with the size of the network. And this is a very important property because it tells us that, for instance, information and knowledge in this network can spread very fast, but also it tells us that pandemics, as we saw a few years ago, or diseases can also spread very fast. So in one sense, it kind of makes our social system, knowledge system very robust, but in the other sense, it makes them more at risk due to certain bad things that can happen in them. What is the distance between two nodes? The distance between two nodes is the number of edges that have to pass to actually come from node I to node J. So for instance, if we look at the distance between nodes 9 and 8, it's 1, obviously. Distance between 9 and 0 is actually 2. Distance between 9 and 2 is 3, okay? What is an interesting thing for complex networks is that you can have many paths between two nodes, and not all of them are of the same size. So this means, for instance, you can see that from 9 to 2, the shortest distance is 3, but you can also have a distance 9, 8, 0, 7, 2. So this is a path, and the distance or the length of this path is actually 4. So you can have different paths between two nodes, and they can be of different sizes, but usually what we are interested in is to look at the shortest paths between two nodes. And in 1960s, I think, Milgram actually looked at this between people in United States. He devised an experiment where he sent 1,000 letters. The importance was that he selected 1,000 people who will send a letter to a specific address, so one person in New York, and he said, okay, you can send the letter to that person if you directly know that person. If you don't know that person directly, you will have to choose one of your connections, so one of your peers, send it to them, and then they will send it to that person, but choose that person, your peer, as best as you can, based on your knowledge, if there is a higher probability that that person may know the receiver of the letter. So basically what he done is to conduct this experiment. Around, I think, less than 50% of the letters finally arrived at the destination, and he calculated the average time that letter was resent, so actually number of these links. And what he found out is that the average number between any two people in America is 6. So the path, the average length of the path, shortest path between any two people in America is around 6. So it was very strange because at that time America had several, I don't know, more than 150 million people. So it was kind of strange that it has so lower distance. Actually, today, if you look, for instance, at Facebook network, this distance is even lower, and I think now is approximated at 3.4. So it's very well-connected world, and Facebook has around 2 billion users on it. So it's quite interesting. And actually, module Networkit allows us to calculate these distances. So we will call a network a function that is within the distance subclass or class, and it's called APSP. So this means it finds the shortest distance between any two nodes in the network. So we will call this function. We will run it, and then we will ask what is the distance between some two nodes. So in our case, between 0 and 8 is, of course, as I said, 1. Between 0 and 9 is 2. And we can actually even call the function get distances. So it will calculate all of the distances in our case. And we will look at the matrix of this. So basically, this matrix is a distance matrix. This is the shortest distance matrix. And you can actually get the distance between any two nodes in the network. So the elements of this matrix are the distance between nodes I and j. And we consider that the distance between the same nodes is 0. So that's why there is zeros on diagonal of this matrix. And of course, for instance, the distance between 0 and 1 is obviously 1, and it's shown here. 0 and 2 is, of course, 1. It's shown here, and so on, okay? So this way, you can actually calculate the exact distance between any two nodes in your network. And now you can go through this and find the longest, shortest path. And this defines the diameter of your network. But in this case, nice thing is that they already have written function, and then you can do it and use this function again. And our network has a diameter 4. Actually, this is, I would say, a very, very large diameter for a network that has only 10 nodes. But it was devised in this way as a kind of just show. But actually, you can look at this kind of things, and you will see for our next example, real example of networks, it has a very different, a much smaller diameter compared to its size. One more thing that I would like to tell you about is actually, we often looked at the assortativity index. So our assortativity index actually tells you how the nodes of different degrees, for instance, in this case, are connected with each other in the network, okay? So this means it tells you whether the nodes of high degree are also connected with nodes of higher degree, or they're connected typically with nodes of lower degree. As you remember, we have this very heterogeneous network, and this can tell us a lot about the way how the network grows, like a clustering coefficient, for instance. In this case, we usually focus on degrees of neighboring nodes, but actually you can also look at other different properties. For instance, if you have males and females, it can also tell you how people of similar gender how people of specific gender are connected with each other, whether it's typical to have more people of one gender have friends of the same gender or different gender, and so on. So it tells you about the similarity of people to whom your nodes are connected. And in this case, we call it a assortativity index, and this assortativity index goes from -1. So this means totally different class of, or totally different thing of people connected with each other. So this means, for instance, if assortativity index is negative, This means that nodes of higher degree tend to connect with nodes of lower degree. And this is actually typical for biological and technological networks, but on the opposite situation, when you have a sortativity index that is very high, so it's in a positive sense, this index tells you that we have an assortative network, and then this assortative network means that nodes of similar degree tend to connect with nodes of similar degree. Social networks have positive and relatively high assortativity index, which tells us that people who are popular have tendency to be friends with popular people, and people who are less popular have tendency to be friends with these less popular people. So this is kind of tells you what is how your network patterns of connectivity tend to be like. Okay, so there's no open questions, so I can maybe continue with some real example. And for this situation, I actually chose to represent a network that is from a large Stanford case. Sorry, I want to connect with my drive. So there is a Stanford large network dataset collection. And if you want to study different kind of social networks, this is mostly focused on social, but there is some technological, there are no biological networks, unfortunately. You can look at there, and there are many data sets from different kind of online communities, from LiveJournal, from Wikipedia, from Friendstar. There are even networks that don't, social systems that don't exist anymore. But there you can really find different kind of data set, different kind of types of networks. Actually, there are types of networks where the edges can be positive or negative. So sign networks. There are networks which have the temporal stamps and so on. So take a look. I left the link toward this. But if you want to study any type of, especially in the case of social systems, then you should look at this, because it can be quite interesting. You can find the interesting data sets. For this occasion, I actually choose YouTube edges network. I'm a little bit limited with GPU selection here, and this network has around 1 million edges in it. And I actually took this network, it's kind of clear, but I also shared the data with you. I only relabeled this network to be easier for us, but it's the same data set that you can find there. And I'm using data frame to actually load this network. And as you can see, this file is very simple one. So you have a source and you have a target. So this means that you have basically a source of an edge and a target of an edge. In the case of YouTube, because it's a friendship network, this network is undirected network. And this means that actually, usually the edge is only represented once, but it's actually a symmetric relation between nodes and between nodes belonging to that network. And here I wanted to actually upload this network to our system. So first I'm going to look at how many nodes I have in my data. I will first get the list of nodes in the source column, list of nodes in the target column. I will merge these two lists, sort S2, and then actually look at what is the largest ID and what is the smallest ID. So it's 0, of course, and the largest ID. So this tells me what is the largest ID of the node I'm having in my network. And the size of my network is actually this ID plus 1, because I'm starting from index 1. And now I'm going to actually assign my network. So I'm going to, again, create an object graph. and I will add 1,134,890 nodes in my network. Then I will use a very simple way to upload my my list. There are other ways here. There are certain there are faster ways, but you have to actually rewrite your edges list and so on. And to be honest, I'm not very sure that there is not some mistake in this. So for these reasons, I actually decided to use a very simple approach, and that's through add edge. So I'm going through each line in my pandas, and I'm adding source and target. Basically, I'm adding links through this. It will take a little bit of time for this. And you can look at Networkit documentation, unfortunately. So for instance, in Networkit, we have a very simple way of just transferring the data from pandas to our graph and actually selecting what type of data we want and so on. Unfortunately, this is not that well developed in Networkit. And it would be nice to have this in the future as an option for this. They use other graph forms for this, but unfortunately, I didn't have very good experience with these graph forms, because it takes a lot of time to transfer my network to these graph forms, and then the time I'm actually using to upload my network is just much less than actually time to transfer my graphs to these forms. Do we have any questions? Ah, there is a chat. Sorry. Okay. Anyway, while we are waiting, I showed you in the upper example on a very simple network. I show you very step by step, calling different kind of functions for the properties of our network. But the beautiful thing with Networkit, I have to be honest, is that there is a function called overview, and this is function here, and this function gives you a very basic but properties that are usually things that you're asking when you are working with unknown data set in some sense, okay? So what you will ask yourself is that how many nodes and edges my network has. As I said, our network has 1,134,890 nodes. That's expected. And it has, as you will see, 2,987,624 links, so number of edges. And this is exactly the length of our data frame function. Besides this, it will tells us what is whether our network is weighted, whether our network is directed. In our case, of course, none of this is true. So basically we get the false in one sense, false in the other situation. In a network, it can be disconnected. It can have isolated nodes. So this means the nodes that are not connected with any of the rest of the nodes in the network. So usually these isolated nodes can represent a lot of problems when you're analyzing networks. So for these reasons, we want to know whether we have them, and the function overview will get us this. We will look at whether we have self-loop. Self-loop is a link that goes from node to that node again. So in this case, we see that we don't have this kind of things, so it's good. It's a very simple network. And then we will look at the density of the network. Density of the network is the fraction of existing nodes compared to the all possible existing links that compared to the all possible links that can exist in that network. And what is an interesting thing is that actually most of the biological and technological networks, but also social networks, are actually very sparse. So this kind of gives us one more perspective when we say that they are small. So they have relatively low diameter, but they can have very, very low number of links. So they're sparse in one sense, and they have very low diameter. This means that kind of this network growth within an idea to have very efficient transfer of information in the network. Besides this, it can tell us this global clustering coefficient. So in this case, it's 0.08. So our social network, while it's social YouTube, it's actually also technological network. It's kind of based on technology. And this kind of tells us that our social technological network is more technological than social because it has a relatively low clustering coefficient. We can get an information about a minimum degree, so it's 1 because we don't have isolated nodes, and the maximum degree is 28,754 nodes. So this means there is a person or an account in YouTube that in this case has like almost 30,000 friends in YouTube. For people who actually, for instance, look at Twitter and also now for YouTube, you know that this number can be even higher than this. So this is not unexpected in the case of these techno-social networks. It also tells you the average number of friends or nodes that's on average a node is connected. But actually this average number doesn't tell you much because the distribution, as you will see in a few steps, is very broad. So the average doesn't actually tell us much about the system. And as I said, this is more technological than social network, not just by clustering coefficient, but it's also almost disassortative. So this is relatively low disassortative index. We can also say this network is basically uncorrelated. So nodes of high degree can equally connect with nodes of lower or high degree, and nodes of low degree, of course, can equally connect it with nodes of high and low degree. So this tells us that this similarity in the sense of number of friends doesn't apply in the case of YouTube network. So basically here we talk about uncorrelated network. And as I said, this network is connected. So this means that it's not fragmented. So this means that there is a path from any node toward any other node in the network. And we say that this network has the largest connected component that kind of spans through the whole network. And the size, of course, in this case of this largest connected component is exactly the same as the size of the network. And now we can look at degree distribution, how it looks like. I said that it's power law. Here you can see how you can actually calculate this degree distribution. I didn't fit it because here we don't have actually how to say, we don't have a code that will help us to fit this degree distribution power laws. Determining the exponent on power laws is very complicated thing. But here the exponent is actually around 2. So you can see that our network is kind of barely belonging to this very heterogeneous networks, but still it belongs. And actually we see that we have very large number of people. We almost have, I don't know, this is not a million, of course, but almost 50% of people actually have one friend or one friendship or one connection. And then we have, as I said, one node that has almost 30,000 connections in the system, but it's not the only one. As you can see, there are many of them that have between several hundreds and and several thousands of friends. We can also look something else. So associative index is just one thing, but sometimes we want to actually understand how our network or how these degrees, what is the average degree of their neighbors. And this can tell us, on one sense, the assortativity index tells us on average whether our network is assortative or disassortative. And as we see, our network is basically uncorrelated in this case, and that would expect that the average degree of the first neighbors does not depend on the degree of a node. But let's see whether really this is the case. And as you will see here, so I gave you this function because unfortunately the Networkit doesn't have this function. Networkit says it, so I had to write it myself. And it would be nice to have these kind of things in the future in this Networkit function, but in this Networkit module. But as we see, actually, the average degree of the node with degree 1 is very high. It's almost, I don't know, this is few hundreds, okay? And as I said, what would we expect is to have a very flat line with uncorrelated networks, but this is not the case. Our network is basically uncorrelated for nodes with several first neighbors, so with degree between 0 and between 1 and 10. But then as we increase the degree of nodes, this average node of the average degree of the first neighbors kind of starts to decrease. So this means that for higher nodes with higher degree, our network is actually a kind of disassortative. So this is a kind of expected thing that we see, for instance, in techno-social networks. So no networks that are kind of embedded in technological space. Let's see about the clustering. So we saw that we have nodes with, we can do the same thing for this. And we can actually look at how this clustering coefficient, the average clustering coefficient, depends on nodes degree. And we can calculate the same thing. So here's the function. Again, unfortunately, we don't have this function, so I wrote it as a function for this that allows me to average the clustering coefficient of nodes of certain degree, basically. So I can actually see how this clustering coefficient, the average clustering coefficient, depends on nodes degree. And what this tells me is that actually my average clustering coefficient decreases with the degree of a node. So the more connections a node has, there is a lower probability that its friends or its neighbors will also be connected with each other. We see, for instance, that for this, the highest node with almost 30,000 connections, its clustering coefficient is below 0.001. So it's very, very low. Okay, so this means that only few of its friends are connected. Actually, this is something that you can really, really see in many networks. Usually a clustering coefficient decreases with the degree of the node. The only difference that we see is typically in real social networks. There, it still decreases, but not as fast as in this case. So basically, this kind of tells us what properties of the network are, of our social network, and then we can actually look at other things in this system. I didn't put the diameter of this network. The reason is that it really takes a little bit of time to calculate this, because it has to first calculate all shortest paths between any two nodes, and we have more than 1 million nodes. It's faster than Networkit, believe me. I tested it, but it still takes some time. So I didn't put it, but you can play with it when you have time. And the last thing I would like to talk in next 20 minutes is a community detection. So if you're a data scientist, you probably have experience with this k-means clustering, where you try to find in your data set, which is in some n-dimensional space, you have data points, and then you try to see how how these nodes or these data points are clustered in space, and whether they are clustered in space. The same thing we see in complex networks. So what we saw is that complex networks are not just heterogeneous on a local level, so these degree distribution, assortativity, clustering, and so on. But we also saw that they have these heterogeneities on, we say, mesoscopic level. So this means that when you look at a network, you can see that there are a group of nodes that are more densely connected with each other than with the rest of the network, okay? In complex network theory, we usually say that these groups of nodes are communities or modules, and they are typically emerge as a consequence of some process in the network. For instance, in the social networks, usually these communities represent some specific locality or some specific some specific thing that happens in the system. For instance, if you look at my Facebook network, my ego network, and you look how my friends on a Facebook are connected, you will see that I have several of these clusters. One of them is from my hometown, where I went to my elementary school and my high school. The other one is again here in Serbia, but these are my friends from faculty, from university, and after that most of us went to work here at the Institute of Physics Belgrade, or we are somehow connected with each other because we are quite small community. So this is the second community that shows that my friendship network is kind of professional related and also related to different parts of my different eras of my lifetime. Then I moved to Slovenia to do my PhD. So the third cluster is related to my friends that are from Slovenia or somehow related to this period of my life. Then I went for postdoc to Aalto University. And then again, you can see really that these people also know each other and they create network. And now I came back to Serbia and I have a little bit different activities, not just research, but also startups and so on. And you can really see these groups, how they emerge through time as a consequence of my different phases of life, but also as a consequence of my professional life that kind of evolved during this time. So these communities tells us a lot of how this system emerged, but it can also tell us a lot about how certain things will spread, for instance, in the system. For instance, if you have gossips, they will most likely first spread within the community and then go out after that and spread through the rest of the communities in the network. The same is for diseases. Very similar is for other things. So basically having communities in the system kind of determines the dynamics of different kind of dynamics on that system, okay? Finding these communities is not simple. There are like, I'm not going to lie, but there is like probably several tens of thousands of different algorithms that you can use. They're mostly heuristic. So there is the perfect partition of the network. Why? Because usually for complex networks, when you define any kind of function of them, these functions have very large number of local minimas, and finding a global minimum is usually very hard. And it's not rare that you will not reach it during using typical approaches, and the larger the network is, the harder it is to get that. And there are also very different ways of defining communities in the network, okay? One of them is the most popular Louvain algorithm, and this algorithm uses a function called modularity. That's a measure that tells you how well your partitions are defined. It's kind of similar to k-means if you're using it. And actually, the Networkit module has a parallelized version of this, so it can find communities quite fast. And this is how you do it. So basically, PLM is a Louvain method. You will call this class community. You will add the graph, your graph. And it can really, as I said, there is a paper actually that shows that maximizing modularity is MP hard problem. Okay, we are working with finite size of the system, but still you can kind of define the resolution that you want to get between your nodes. The higher this resolution, the more you prefer smaller communities in that sense. And you can define here the maximum number of iterational steps. So this kind of puts you in a safe place where you can get your results relatively fast. The more iterations you have, the slower your process will be. And it kind of has several other parameters that you can define. For instance, this turbo, it says it's going to be faster than usual. When you call this, you will also need to run the function again. Then when it's finished, you have to get the partition. It's a special structure that is written in Networkit. It's actually structures, partition, and then you will see how many the number of subsets that you had, okay? So you don't give the number of subsets in advance. The Louvain method determines the number of subsets or the number of communities that are in your network. And believe it or not, because it's a kind of heuristic algorithm, each time it starts from different initial conditions, and this means that it will get different number of subsets in each run. So you have to be aware of this, that communities that you get don't have to be the exact ones in each of the runs. We can solve this through other means like ensemble, Louvain method, and so on. But still, this is something that you have to be aware of. Besides this, you can also use so-called the label propagation algorithm. It's also one way of finding the communities, and I wanted to run both of them because they're parallelized in this case. But as you will see here, we have 4,000, almost 4,500 communities, and actually label propagation algorithm found almost 25,000 communities. So each algorithm will kind of give you different number of communities, and the structure of these communities will be different. So when you choose which of the algorithms you will use for community structure, you need to think about your system, how this system evolves, and what you want your communities to represent to you. And based on this, you will choose which algorithm you would like to look at. And here I wanted to just see how many elements are assigned to these 25,400 subsets. And I wanted to show you actually that with Louvain method, you will get in each run different kind of communities. But as you will see, these communities, while different, they don't differ that much, okay? And there is a measure that will actually shows us this. So now we run it once more, this Louvain method, and I kind of stored it in the other variable, so I can actually compare these two partitions. And in this case, it found less than 4,000 communities, unlike the first time when it found 4,424 communities. Now, I can compare these communities by, sorry, this is something. Oh, I can compare these communities by plotting it. So here I see 3 different lines. So I actually ordered communities based on their sizes. And based on this, I can calculate the ranking of each community, basically, based on their sizes. And the red line and the green line are actually what I found using my Louvain method. So we see that there is some differences between nodes of small communities. So the communities that have 1 up to 5 nodes in them. So there is different, the largest community. So here we can see that there is differences. But then if we look at the smallest communities, their number is almost similar. But if we look at the blue line, that's the blue line is from this label propagation algorithm, and it's quite different. So this visually tells us that there are really differences between our algorithms, but we can actually calculate this. There is a function called mutual information, which I wrote here, and you can use it to actually compare 2 partitions of the same network. I wrote the function here, and also because it uses vectors as so the partitions needs to be written in a specific way to use this function. I actually wrote a function that allows me to kind of transfer my partitions from Networkit to needed form for mutual information. And I will transform first my all of my 3 partitions. So one found with label propagation algorithm, one found with Louvain method, one Louvain method second time when I run it. And now I want to see how my communities compare with each other. So first I told you that yes, Louvain will find different partitions. It will be different number of partitions. This allows you to compare 2 partitions of different number of communities that you will find. But it will tell you if you compare the partitions found with the same algorithm. It will take a little bit of time because they have several thousands of nodes. We see that mutual information is 0.84. So mutual information close to 0 tells us that your partitions are quite different. So they don't have anything similar or in common with each other. But if you have a mutual information, the maximum, so it takes values between 0 and 1. And if you use mutual information to compare the partitions, the value of mutual information close to 1 tells you that your partitions are as similar as possible. So 0.84 is actually not that bad. So this tells us that our algorithm, while it has differences due to different initial conditions, it kind of finds the communities that are in some sense similar. So we have different number of nodes in communities, different number of communities, but still these partitions are quite similar. Unlike that, we can, for instance, compare the label propagation algorithm and one of these Louvain methods, but as you will see, they're very have similar mutual information value of index. You will see that they're quite different. If you go to Stanford, a large network data set, you will see that you have something called ground truth communities. In some networks, even for YouTube, people can declare, for instance, whether they belong to a certain community. You can use these networks so these groups as ground truth communities, and we usually use these data sets to actually test different kind of algorithms. Again, mutual information is in this case used to actually compare the things found by your algorithm with the ones that you found by with the ones that are actually declared by people. What you need to be careful in this case is that while I declared that I belong to some community or some social group in the system, this doesn't mean that dynamics or my activity or my communication with other people is necessarily represented in my membership to a certain social group. So ground truth communities don't necessarily can be observed from the structure of the network. So be careful when you're comparing these results or when you're selecting the specific algorithm, because not necessarily the structure of your system is seen in these social groups that you declared. So in that sense, you really have to think about your system and whether you see it in it like that. I wanted to talk also about the link prediction, but I don't think we have enough time this time, but you will have, Networkit offers very nice algorithms already written in advance based on different kind of indexes that allows you to predict whether, if you don't have a link between two nodes, whether and what is the possibility or probability that these nodes will be, for instance, linked in the future. So look at this, look at Networkit. It's quite interesting, relatively new module. And if you get very interested in that, I recommend you to join and try to actually help develop this module, because I think large-scale network analysis will be very, very popular in the future. So that's it from my side.